Hello there, grade 11s. Time for another video. Oops, this is the summary. This is the end of the presentation. All right, let's get started. So this is about resistance in series and parallel circuits, and I believe this might actually be the first new thing in this unit because the other stuff you should have covered in grade 9. So these are resistors. Hopefully you've seen them before. You should have seen them in the introduction to this unit that you built online using the online simulation, but if you didn't do that, maybe you haven't seen them before. Anyway, their whole purpose is to introduce resistance into a circuit. Now, lots of components of electrical circuits introduce resistance. Light bulbs introduce resistance. When you built the circuit with the dog and the paperclip, dogs and paperclips probably have resistance too, but that's not their main purpose. Resistor is the component whose main and only purpose is to introduce resistance. Now, the colors actually mean something. They actually represent how much resistance a resistor has. I'm not going to bore you with all the details. You can look it up if you want, but basically they're like place values. I think one of the bands is like the thousands place, and one of them is the 10,000s place or something like that. And the colors represent different numbers. So you can work out the resistance of a resistor if you know the system, but you don't need to know it. You can look it up. It's pretty easy to look it up. So this is the symbol for a resistor. Every time you see this, that's what that represents in a circuit. So really what we want to study here is how to find the total resistance of a circuit depending on whether it's series or parallel. Now, if you're looking at this circuit, you're probably already thinking to yourself the correct answer. It's nothing fancy, nothing complicated. You just add up the individual resistances. And so in this case, it's 14 ohms. And that, I think, is pretty straightforward. And here's the formula. So you just add up R1 plus R2 plus R3 plus etc. as many resistors as you have. Now, here's where I'm going to change things up a little bit here. This is a little bit subtle, but I'm actually going to stop talking about total resistance. So take this word total and just discard it from your brain. Forget it ever existed. Let's think about equivalent resistance. It's a different way of thinking about total. It kind of means the same thing, but try to change your mindset so you're thinking in this way, okay? This is what this means. If you drew a circuit that was equivalent to this given circuit, but it only had one resistor instead of 3, what would be the resistance of that one resistor? Actually picture it. Visualize that new circuit. I'll show it to you. So this is what it looks like. This original circuit that I gave you is equivalent to this circuit that only has one resistor, but that one resistor has 14 ohms instead of 5, 7, and 2. And so if you built these two circuits, they would basically function the same. They would have the same amount of resistance. And they would actually have the same current and voltage as well, because we're still using the same battery. And so they have the same voltage. And if they have the same resistance, then according to Ohm's law, current is equal to voltage divided by resistance. They must have the same current as well. So these circuits are equivalent in terms of how they function. They're not identical because they don't look exactly the same. They have different components, but they are functionally equivalent. Now, how does resistance work in parallel circuits? It's a little bit more complicated. This is the formula, and it's based on fractions, specifically reciprocals. So when you take something and then flip it upside down so that you have 1 on top and then the original thing on the bottom, that's called a reciprocal in math. So 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3 and so on for as many resistors as you have in parallel. So in this case, I'm using the same numbers as before, but it's a different circuit because it's parallel instead of series. 1 over 7 plus 1 over 5 plus 1 over 2. Now, in order to solve this, you have to make a common denominator if you want to add up fractions. The common denominator for 7, 5, and 2 is 70. So change these to equivalent fractions and add them up. 59 over 70. And then you're going to want to flip that upside down. Why? Well, because if you look at the left side of the equation, 1 over RE this is not actually solving for RE. You need RE to be on the top of the equation if you want to actually figure out what it equals. So you have to flip the left side and the right side. And so you get RE equals 70 over 59, which approximately equals 1.19 ohms. Just checking my audio levels. Yeah, I think I'm looking pretty good. Okay. All right. So here's what this means. This parallel circuit with these resistors is functionally equivalent to this much simpler series circuit with only one resistor, and that one resistor is 1.14 ohms, which might be kind of surprising because it's much less resistance than any of these resistors over here, but that's just the way the math works out. Trust the math. So these circuits are functionally equivalent to each other. Once again, they're not identical. They don't look the same, but they kind of work the same, at least in terms of their total resistance. One more example. So this is a complex circuit. And what I mean by that is it's neither series nor parallel. It's kind of both and neither at the same time. So you'll notice that these two resistors, R2 and R3, are in parallel with each other, but they are in series with R1 because every single electron that comes out of the battery must go through R1. So that's a series resistor. But then over here, it splits into two paths, and the electrons can go either to the right or down. And so it becomes a parallel circuit there. So in order to analyze the circuit, we have to apply rules of both series and parallel circuits in at different steps of the analysis. So how to solve it, and this is the basic procedure we're going to follow, is to find the equivalent resistance of R2 and R3 first as a parallel pair. And then once we know that equivalent resistance, we can use the laws of series resistance in order to combine that number with R1. And then we can get the equivalent resistance for the entire circuit. Okay, so let's get to it. So let me just first point out that when I write R23, this is not 23, it's 2 and 3. So the equivalent resistance of resistors 2 and 3 is equal to 1 over R2 plus 1 over R3. Plug those numbers in, find the common denominator, 12. Change the numerators appropriately. You need to know how to do that. Add up the numerators, and then flip the whole thing around. So the equivalent resistance of these two parallel resistors is 1.58 ohms. Let me just pause here to redraw the circuit in a simpler way. So this original complex circuit is equivalent to this series circuit with two resistors, where I've replaced the two parallel branches with this one resistor of 1.58 ohms. But that's not simple enough. Let's make it simpler. So these two resistors are now in series with each other. And so applying the law of resistance for series circuits, you add them up and you get 3.58 ohms. And so now this can be redrawn one more time to be even simpler. And so this original complex circuit is equivalent to this simple series circuit with only one resistor, which is 3.58 ohms. And that's it. In summary, the concept of equivalent resistance is important. Make sure you think about that. Try to wrap your head around what equivalent resistance means. And then in series, the total resistance or the equivalent resistance works like this. You just add up each resistor individually. And in parallel, you have to do this more complex equation that involves reciprocals and fractions. And finally, just make a note of the fact that there are complex circuits that are neither series nor parallel, or you can say they're both series and parallel. And you have to apply rules of both series and parallel circuits at different steps of the process. And it's kind of up to you to figure out what that strategy is exactly, depending on the layout of the circuit. Okay, that's it. Thanks for watching.